Okay, I think we finally have everything together. Good morning, everybody.
Morning.
This is the first class. Some of you have had class before, but if this is your first class, welcome back. Even if you're not your first class, welcome back. Hope you had a good summer, and looking forward to fall semester and learning about some hydrogeology. This is groundwater and contaminant transport class, so hopefully that's what you're here for. I'm Larry Murdoch, and I'll be the instructor for the class. One thing to get out of the way as we get started. Next class on Friday, not going to be here. It's going to be online. As soon as class is over, I'm headed to the airport and going to be go to Oklahoma for a couple days, and won't be here. So either I'll do it online from Oklahoma, or I'll post a recording of the class. I'm not sure. We'll see, but it won't be here. So what I want to do today is just get started and kind of do some introductory material, tell you about what the class is going to be like. And so I thought what we could do is get started with, you're all going to spend a chunk of time this semester learning about groundwater and contaminant transport. What should you be able to do after taking this course? So the big picture learning outcome. So a few years ago, we had us put this together, and so this is what I came up with. I think this is probably on the syllabus. Here's what I want you to be able to do: working knowledge of the hydrologic system. So that'll be the big picture, and particular emphasis on problem solving related to groundwater contaminants. So this is the name of the course, right? So we're going to do that, but we want to have a bigger picture of the hydrologic system. And the thing that I wanted to put on here in particular was the problem solving aspect. Basically, problem solving is kind of the motivation for somebody paying you to do something, right? Somebody's going to pay you to solve some problems. So what I want to do is get you prepared to do some problem solving to kind of get ready for your next chapter in the professional world. We have groups with a geology background and groups with a civil engineering background in the class, and both of those backgrounds are well suited and have a lot of applications for groundwater. Some with a direct focus, where the specialty would be in groundwater and contaminant transport, and in other cases, it'll be using groundwater and knowledge of groundwater as kind of as a secondary thing to support other activities. For example, in civil engineering, if you're doing foundation engineering, that may be your focus, but the role of groundwater will be important for many foundations. So we want to be able to understand the system in order to solve problems related to the system in meaningful ways. So I wanted to start out with a picture of home. So how's that look? Should I try to turn the lights down a little bit? It's a little bit glary. What do you think? Okay?
It's fine.
Yeah, okay. All right, so this is the picture of campus. And here's the stadium. So we're over here someplace. And my office is there in Brackett Hall. And I've indicated a few other places here. This is the motor pool, the Save a Ton Sunoco, some other gas stations here. This is the former dry cleaner up here, facilities maintenance. And so I put all of these places, well, I don't know. Why did I put those places on there? What's kind of the common, I mean, most of them are gasoline places. Then there's also that dry cleaner up there. So those are places that are, they're storing liquids that are contaminants or they're potential contaminants. So gasoline is hydrocarbons. There's probably the number one most common contaminant that is in groundwater that is from man-made sources. And you can see why, because there are many gas stations just within a mile or two of where we are now. There's also this dry cleaner. I think actually this dry cleaner is no longer here. I think they've done a lot of building since then. But there used to be a dry cleaner here. And dry cleaners use a solvent to clean clothes. And I don't know if you've ever gotten the clothes back from a dry cleaner, they have kind of a sweet smell to them. That's a solvent that works really well at getting the dirt out of clothes, but it's also a contaminant that's carcinogenic. It's also a compound that's carcinogenic. So when dry cleaners store that stuff that they use to clean the clothes, they have it in tanks. Just like gas stations have gasoline in tanks. And it turns out that turns out that tanks almost always are going to leak. So up to the, I don't know, the 80s, 70s, 80s, they made tanks out of steel, put them underground. And if you do that, then the steel corrodes underground and eventually it gets holes in it and leaks. So virtually all of the gas stations that were kind of older gas stations have tanks that leak. And back in the day, they didn't really know any better. They would come in, fill up the underground storage tank, and then come back the next week. And they weren't really keeping track of how much was there. So if they had a little bit leaking out, they just top the tank off. So the gasoline contamination associated with gas stations is widespread. And then also, similarly, many dry cleaners that have been around for a long time have contaminant, they've leaked and they have contaminants associated with them. So it's a problem that is in our neighborhood. There's a place, let's see, up here. So this is 123. And there's a former gas station here. It was here when I first came here. It was old then. And so they tore it down, but that place, that leaked and formed a plume that went back underneath this neighborhood here. So that was kind of a big deal. For a while they got it fairly well cleaned up. But groundwater contamination is a local problem. So I want to show you an example it's not local. This is from Paducah, Kentucky. There's the Ohio River there, so it's close to the Ohio River. And this is another example of a groundwater contamination plant. This is called the Paducah Gaseous Diffusion Plant, and that's it right there. So it's an industrial place. There's a scale, so it's pretty big. It's around a mile across. And it's an industrial place that is similar in some respects to many industrial facilities. It's unusual though in other respects because this gaseous diffusion, what they mean by that is they would take uranium and put it into a gaseous phase, and then they had a process where they would put it down this tube and it would diffuse out, and they would enrich the uranium for fuel, and also this is how they would make uranium enrichment for weapons. So this was done there. So I mean, it's an industrial place, but that's kind of an unusual industry to be involved in. But they had a lot of activities and they have a lot of problems associated with that. So one of the things that happened here is that there were spills and leaks in this area of a solvent called trichloroethylene. That's this stuff that's abbreviated here. And this technetium, this is a radionuclide that occurs as a result of the processes they were doing. So they had this stuff around, and they had spills right here, and that ended up causing some problems. So the spills occurred right here. This is the facility, and you can see all this is not as developed as it is out here. This is all farmland. This is on high ground, and then there's some streams that come here and go down, and they're tributaries of the Ohio River. So they found that there were some leaks here and spills in this area, and then that would pose some questions that it would be addressed by people with backgrounds in groundwater and contaminant transport. So one of the big things that drives problems in groundwater and contaminant transport is the risks that these contaminants pose. So there are risks to human health, there are risks to ecosystems. So what are those risks at this particular place? These contaminants, those two things that I showed you, those are carcinogenic. So if people or ecosystem gets exposed to those contaminants, there's an increased cancer risk. So that's a primary driver of the risk. And then one of the next questions would be, well, how would exposures occur? How could that happen? And it could happen if there are contaminants that are moving to some place where the people or ecosystems are. So that would lead to the next question: how are the contaminants moving? Where are they, and how fast are they moving? And what can be done to improve safety? So these are all questions that would be essentially posing a problem that would be something that would be solved by groundwater professionals. So here's one of the things that you would do to start off answering some of these questions. You want to find out, where are the contaminants and how fast are they moving? So what happens is the groundwater infiltrates here, and takes the contaminants downward, and then there's a groundwater flow system throughout underlying this whole area, and the contaminants get into the groundwater and flow generally down there towards the river. They're going to flow locally towards streams, and then also towards the river. So one of the things that's done is to go out and use a drill rig and poke holes in the ground and take samples and measure the contaminant concentration in the groundwater. So that was done. And then the concentrations of the trichloroethylene were contoured up. And here's the source. And you can see these lobes. These are groundwater contaminant plumes. So you can imagine that there's a source of contaminants in here, and the groundwater followed this path and took the contaminants along with it. The groundwater also is flowing this path here. So in this vicinity, this is what's called a groundwater divide, because on this side of the divide, the groundwater flows that way, and then on that side, it flows this way. And you can see two plumes as a result. There's probably another one here that looks like it's probably not fully understood, because there probably is some kind of a connection. There's also another little plume here, and you see how it goes and just kind of stops. Well, what's happening, there's a stream in here, so this is discharging down the stream. It goes down and comes back up and discharges to the stream. This is going down, stays in the subsurface. You see that kind of weird shape? It looks like that. So this is a stream here. that's a tributary to the Ohio River over here. And the plume goes down and is discharging to this stream. So it's coming back up and discharging to the stream. This one is not discharging. So this is a big area of contaminated groundwater. Exposure could occur if there are people that have wells in this area that they're pumping this water out. And also there are exposures to the ecosystem here where these plumes discharge to the streams. It impacts over 2,000 acres of land. And this is the boundary of the site here. So this is owned by this place, and you can see that these plumes are going off of the boundary of the site. So that's really the worst case scenario. And because it means that it's impacting places that this facility no longer has control over. So that'll set in motion a bunch of efforts to try to understand the problem and then also figure out what to do about it. So here are these risks. You could see the exposure could occur by wells or by discharge to the stream. And one of the things that we want to know is how fast is it moving? So there would be various tests that we'll learn about to describe how fast groundwater is moving in the subsurface. And then what can be done about this? Well, there's a large field that many of you will likely go into or be aware of that involves remediation or cleanup of contaminants. So you find out what the problem is, like this, and then you come up with solutions to either remove the contaminants or mobilize them or destroy them. So this is the technetium, and you can see that it also forms some pretty large plumes. Okay, so in addition to understanding groundwater contaminant plumes, there are a variety of other things where hydrology is going to be important in other areas. So one of them is just domestic water supply. This is providing water to people's houses. And I don't know, does anybody here have a well that provides water at home? It turns out, according to the statistics, about half the people in South Carolina have a water well. So it's fairly common. Understanding how that works and what the risks might be is one aspect of hydrogeology. Industrial uses for water. I mean, sometimes water is just taken and bottled and sold. So that's one way to make a profit out of water. But there are various industrial uses for cooling, for example, as shown here, and understanding the water supply issues associated with providing water as for those applications is important. So here, water has some value. This is a building that's a foundation that's being built. You can see that's a excavated kind of a deep pit, and there's this canal right here. So this is a place where water would be a nuisance, and in fact, a pretty hazardous, a potentially hazardous situation if that water were to get into this excavation and flood it. So understanding how to keep the water out will be also an important application. Sure. A lot of applications, there are a lot of agriculture needs water for irrigation all through the Midwest. I don't know if you can, yeah, this is really small, but there are lots of green circles here. Maybe in the front row you can see these green circles. These are from Central Pivot Irrigation System, where at the center of that circle is a large capacity groundwater well. Typically the way it's done is pump the water out of that central pivot location and then spread it out. And it allows you to grow water or grow crops in areas where the water supply is low. Here's kind of a cool image. This is northern India, and this is a gravity anomaly that was measured from satellite. And gravity is the strength of gravity depends on the mass of the Earth, right? So if the mass changes, then the gravity changes. So they can measure gravity with super high resolution. And what they found was they made a series of measurements over the years. And what they found was that the gravity was changing, and that's an anomaly where the force of gravity is decreasing as a result of a decrease in mass from pumping out groundwater. So it's high enough resolution so they can actually measure the mass of water that's been removed. So that's pretty cool, but what's pretty sobering is that this is where this is the main agricultural area in India. So India grows a big portion of its food in that area, and it receives very little recharge. So they're essentially mining the groundwater that's there to use it to grow crops, which is great now. But if you're mining it, it means that it's a finite resource, and you're gonna eventually deplete it. And if you start to run into depletion problems in a place where it's a major food supply for a major country like that, then that has some potential big implications. And then also ecosystems. So we think of aquatic ecosystems. Clearly that's going to be dependent on water, but really all ecosystems, even the terrestrial ecosystems, are going to be dependent on water for the critters that live and actually utilize the water for food, but then also just for water supplies. So there's a wide range of potential applications for things we're going to learn in the class. There's also kind of a broader perspective on this. These are some of the things that we're in the department we're getting interested in that are groundwater related. So geothermal energy, this is recovering energy from the subsurface, often through hot water, storing energy in the subsurface like a battery. So this involves putting heat into the subsurface, and if you're going to do that, then you need to understand how the water is going to interact. We have a project ongoing right now that's out by the water tower, west of town. It's near the water tower. We're heating the ground up to we've got a few places where it's over 100 degrees C. We boil the water off. We're heating it up as a way to store energy like a thermal battery. The water played a big role in heating up the ground, and then also carbon sequestration to remove carbon from the atmosphere. It's taken, the CO2 is removed and then put into the subsurface and stored, and that's also an important application for the kind of skills that we'll be learning in class. So the big focus is going to be on hydrogeologic problem solving. And in order to do that, we're going to learn some principles, how the way hydrologic systems work, some names. We're going to have to just memorize some names because we're going to have to communicate about these things, and we got to be able to know what we're talking about. We're going to have some data from measurements and learn how to analyze the data. Various techniques from the field, some equations. We've got a couple of different computer models that we're going to use. Groundwater, you can simulate the flow and transport of groundwater fairly well with computers, so we're going to utilize that. And then we want to synthesize that and put it all together. Here's an example of computer simulation of a plume. So there are some contaminants that go in here, and you can see that groundwater is moving in this direction, but it's also moving downward and has that kind of lobe-like shape. And then there are various field techniques that we'll learn about to how to determine where contaminants are, and then how flow occurs through porous media. So that's kind of the overview of the things that we'll be doing. And the format Most of the format will be a lecture like this, where we have a well field down in the Clemson bottoms, and we'll be meeting there for some exercises later on in the course. We have a couple of different software packages that we want you to learn to do some groundwater modeling. So that'll be an aspect. The software, we have site licenses, so you should be able to run it on your own computer. All the class material is on Canvas. So this PowerPoint, everything that we'll use, the handouts, is on Canvas. If you want to check out the PowerPoint, go to the place to get the most recent version is if you go to Files and go to, I don't know, Lecture 2025, they're in there. I also have modules set up, and they are linked to PowerPoints there, but I don't know, I'm not sure that those are necessarily all updated. There's a lot of links. If you want the most current, go to Files. I've made a bunch of videos through the years. I have a YouTube channel where they're all posted, and I'll use some of them through the class. There are some that I'll link to officially. There's others that might be just a useful supplement. There'll be homework that'll be due every week, and we'll submit that on campus. There also will be a project that's required for graduate students and optional for undergrads. Undergrads can do it for extra credit. That'll be done at more towards the end of the class. So here's the syllabus. We have a textbook written by Fetter. Here there'll be some readings and some assignments from the textbook. I'll have office hours after class on Wednesday, except today. I won't be there today. But normally I'll be in my office. But really, you can. If you want to talk, you want to send me an email anytime. And also I'm open to, make an appointment to meet you either in my office or do a Zoom link, or we can figure something out. So just feel free to contact me about questions. We'll have some 2 midterms and a final, and then homework, quizzes, and we have a distribution here. The homework, there'll be homework approximately every week, and they'll be due on Wednesdays typically. They're on Canvas. I have on page 3, I've got kind of an overview of the course with some due dates. I may change the due dates depending on stuff that happens in the course. So the final due date will be on Canvas. It may change a little bit from what's printed. So yeah, I just added this AI and phones. So I'm kind of naive about AI and ChatGPT. And last year, I let everybody use their phone in class, and there was a guy that had not doing too well in class, and I had some questions that were definitions. One of these definitions was like really long and involved and really, really eloquent. I'm like, wow, I wasn't really expecting that from this guy. So I had heard about like ChatGPT, so I put the word into ChatGPT, and it was like word for word. So I've since learned a little bit more about ChatGPT, and I don't know, I have mixed feelings about it. I've been using it a fair amount, and it's pretty good, but it does make a fair number of mistakes. So I think that there are probably some good applications for it, even in this class. For learning, it'll do quizzes, it'll do, prompting, that kind of thing. My feeling is basically I expect you to know everything that we're doing in class, and for homework, expect you to know that on the exam, and there'll be no phones. You can't use your phone, you can't get to AI for the exam. So you need to know all the stuff. If you want to use AI to help learn, that would be great. I would encourage that. But ultimately, you're gonna need to know how to do it without that help. And I know in some cases, the help is, I don't know, mixed that. I guess also I should say, when I was using ChatGPT, I was asking it questions, type of questions, and I mean, some of them were right, but some of them were kind of the average, some kind of average response. And I guess for this class, for definitions, there'll be some definitions and some aspects that I'll have for different terms and different processes that are maybe a little bit different than the average. And I'll explain why I want to do it in a particular way. So for the purpose of this class, I want you to use my definitions rather than what you might get from ChatGPT. There won't be a lot of that, but there will be some. And I tried out ChatGPT, and it wasn't. It was using more of the general definition. So I'm going to try to train it to get it to use my definition, but we'll see. So there'll be, yeah, I don't know. There's a lot of stuff here. Attendance. So the kind of policy is if you have more than 3 unexcused absences, you will receive an F for the grade. I mean, that's pretty harsh, but this is kind of the official policy. If you're not showing up for class, you're going to have problems keeping up. But I guess one thing is that you can see there are a couple of folks taking this online. So the classes will be recorded. So if you need to miss, there'll be a way to get the material. But if you need to miss, let me know. So it's not just not showing up. Okay. I have a lot of details here. You can read through it. The grad students are going to have a project that'll be the primary difference between grad and undergrads. And then here's a listing of the topics for each day. This is when the homeworks are due, and here are the readings. So this is the first cut at this, and what usually happens is I end up changing it a little bit as we go through the class, but this will be pretty close to what we'll do. Okay, so any questions about that? Yeah.
I think it's in the AI and phone section, you mentioned needing to bring a calculator to expand, or you found the full graphing calculator, or do we need like a little more function?
Well, so you'll see, I guess, you'll see the kind of, you'll need to do some calculations.
Yeah.
So we're not gonna have to graph it,
Yeah.
but you will need to have some, some functions, some contaminant functions. If the little one has that, then I think you'd be good. If it's just addition, subtraction, that kind of thing without any special function, that might be a little light. Yeah, you will need a calculator. So hopefully that's not a burden. I mean, everybody used to have calculators, but I don't know. The phone works really good for a calculator, and that's why I was letting everybody use the phone. But I don't know, AI kind of threw a wrench in that. Okay, any other questions? Yeah.
You said so the only difference in undergrad and grad is the project,
There's
and that's part of the homework grade. That's what gets thrown into. I thought that's what I read.
Yeah.
I just didn't know how much of
Oh,
homework grade it would actually encompass. Like if it's
I'll get that set up, and it's not set up in Canvas right now, but I'll do that. It'll be like worth a few homework points. It'll be like 2 or 3 or 4 points in there.
Okay.
So it'll be enough. If you're undergrad and you're considering it, it's enough to like bump you. If you're right on the border of a grade, it'll bump you up. So
Okay.
that's kind of the scale of it.
Appreciate it.
Yeah. Anything else?
You know what the project is yet, or?
Yes, so the project is something that you and I negotiate, all right? So the project is to do something relevant to the class. That's kind of independent work. And typically it involves doing finding some kind of a problem and write a proposal. And then you solve that problem with a groundwater model. So you'll use one of the model tools that we learn in class. That's typically what it involves. So that gives you a little extra experience with groundwater modeling. Okay, so I want to do just a quick overview in the time that we have left and talk about the hydrologic cycle from the hill slope to the watershed scale. And I want to introduce some terms. These are terms that we'll start using next class and just add it to your lexicon. So the water cycle is the big picture of how water moves through the surface of the earth. This is the cycle shown in a nice graphic. And basically what's happening here to cause this cycle to work, you have to have energy input to get this to happen. And that energy comes from the thermal energy from the sun. And that goes and causes evaporation. And we start here at the low point in the ocean. We have evaporation that causes the water molecules to move upward and gain potential energy. And then it rains up here at high elevations. And then this basically has now potential energy from the elevation, and it flows downward and comes back to the coast. So that's kind of the big picture. Along the way, we've got flow that goes in the subsurface and discharges to streams, and then streams are flowing to the ocean. Sometimes the groundwater is discharging to lakes, and in some places the groundwater goes from lakes back into or water goes from lakes back into the ground. Got a variety of terms here, evapotranspiration, precipitation. Those will be some terms we'll look at here in just a second. So one of the organizing concepts in hydrology in general and in groundwater is a watershed. So what's shown here is a surface watershed. And the idea here, these are streams here, and this boundary of a watershed for surface water is typically going to be the topographic divide. So there's a ridge right here, and if you took a beach ball and put it on one side of that line, it would flow. You put it on the green side, it would roll down, get into one of these streams, and go past that point. So this point is really what's defining this watershed. Any beach ball in this area would roll past that point. And here's some other depictions of it. So that's a surface watershed. Now there's another concept that is a ground watershed, and it's similar, but it's different. Because what's going to happen is groundwater, you're going to have water infiltrating into the subsurface, and then the groundwater is going to flow in the subsurface, and it will flow and discharge this stream, and then that stream will flow past this point. Okay, so that's so basically the groundwater shed is the area where infiltrating water would all eventually flow past that point. But what we'll see is that this is the topographic divide, and we'll see that the groundwater divide that marks the boundary of a groundwater shed is different than the surface water or the topographic divide. So this might be the ground watershed here, where that's the boundary of recharge going in here and discharging to that stream, and then recharge over here would discharge someplace else. So what I want to do is take a cross section through the long profile like this. So we'll include the stream and we'll go up to the groundwater divide. And here's that cross section. And we've got a variety of things going on. But what I want to do is this is where I want to draw some stuff on the board. So I want to take a look at the water cycle at the groundwater at kind of a local scale. And we'll look at what happens when it rains and then following a rainstorm. So here's a cross section, and that's the stream, and that little triangle, that means that the pressure there is equal to 0. So that's the surface of the stream. And we'll have a surface in the subsurface that looks like that. And this is the groundwater table. And the little triangle means that the pressure is 0. So the definition of the groundwater table is that the pressure is equal to 0 along that surface. So pretty much guarantee that there'll be a question on the exam, what's the definition of the groundwater table? And it's that it's the place in the subsurface where the pore pressure equals 0. It had a general surface that looked like that. So what's going to happen? Let's have some rain fall on this surface. So the rainfall occurs, and the first part of a rainfall is going to land on some trees, and the rain lands here, and it's intercepted. And it never really makes it to the ground, so it's never gonna enter into what we're interested in for the hydrologic cycle. So it continues to rain, and these places that act as storage for the groundwater or for the rain fill up, and the rain starts to make it to the surface here. So when it first reaches the surface, then it starts to flow across the ground surface into the subsurface, and that's called infiltration. And if you're out here in the rain, standing out here, when it first starts raining, if you're out in the woods, you don't really feel the rain, right? Because it's all intercepted. Then after it rains for a while, the rain starts falling on the ground, but it's falling on the ground, but you don't really see any water at the ground surface, right? Because it's all the rain that is hitting the ground surface is infiltrated. So that's what happens at first. But then what happens if this continues is the water content starts to increase. Sometimes around here in particular, but this is a common thing, that in soil horizons, there's a lower permeability layer that's down like this deep, and that blocks the flow. So as rain continues, the water content increases, and the water content increases, and this can get fully saturated with water. And when that happens, then we can have water flowing across the ground surface. So if you've been out in the woods, after it's been raining for a while, and perhaps a hard rain, you start to see water flowing across the ground surface, but it takes a while. And that's called overland flow. Now, this water that's in the subsurface, it's also going to be flowing. It flows down, but it also flows down slope. So the water that is flowing down slope in the subsurface, sometimes it's called interflow. And sometimes it's called subsurface storm flow. Okay, that's going along in the subsurface. So what happens is this stuff's moving down slope, and the water that moves down slope, it's gonna merge from the subsurface and flow into the stream. And then overland flow, it's also gonna flow into the stream. So if we take these two and add them together, it's overland flow, and this is subsurface storm flow, so this is kind of surface. We would lump these two together and just call that storm flow. And it'll be storm flow really when it's getting to the stream. Okay, well, so that's what happens over the short time scale during rainfall. But this water is going to start to move downward. And well, let's say the rain stops, sun comes out, and this starts to evaporate. So this stuff evaporates, and then the trees start. We have roots down here, so the roots become active, and the trees start pulling the water out of the soil, and that's called evapotranspiration. So probably won't write that again. I'll use ET. So ET is pulling the water out, and for a small rainfall, particularly in the summer when the trees are active, maybe all of the rain that falls gets pulled out as ET. But in the winter, the trees are less active, and you can have water making it down through the subsurface and reaching the water table. So when it reaches the water table, that's called recharge. And that's replenishing the water that is in the subsurface. This is the groundwater here. And the water there's a flow system here in the subsurface that looks like this. So you see this high point? The water is flowing as a result of the slope on this surface. So it's going to flow like that to the stream. And this is the groundwater divide. Okay? This depends on how the recharges come into the subsurface, what the properties of the aquifer are. This would be an aquifer here. And so this divide, it depends on what the subsurface is like, and it's different than where that is. Okay, so that's why the groundwater is different than the groundwater shed is different than the surface watershed. All right, so just two more things. We got groundwater flowing to the stream, and the groundwater discharges to the stream, and where that occurs, sometimes it's called base flow or groundwater discharge. And then what we have now is the storm flow coming into the stream, and the groundwater coming in the stream is base flow. And then flowing kind of out of the board would be the stream. Okay, so that's the cycle. There's some terminology in the handout. So if some of these terms are a little bit new, then check out the handout. Because I'm just gonna assume that you're good with them and we'll go and start using them and I'll see you again on Monday. Well, good.